The universe is vast and mysterious, but we are not blind to its wonders. Light, that celestial messenger, travels across billions of light years carrying with it stories of distant stars, galaxies, and the very fabric of space-time. Light is more than just illumination, it is data, a cosmic language whispering secrets of the cosmos. Photons, the fundamental particles of light, embark on an epic journey from distant objects to our telescopes. As they traverse the vast expanse of space, these photons carry encoded within them a wealth of information. Like cosmic barcodes, their properties, wavelength, frequency, and intensity, reveal the temperature, composition, and motion of their celestial sources. By deciphering the messages encoded in light, we unravel the mysteries of the universe. We can determine the chemical composition of stars, the speed of receding galaxies, and even peer back in time to witness the universe's infancy. Light is our cosmic time machine, allowing us to study events that transpired billions of years ago. However, the journey of light across the cosmos is not without its obstacles. The space between stars is not truly empty but filled with a tenuous expanse of gas and dust, known as the interstellar medium. This cosmic haze can scatter and absorb light, dimming and reddening the starlight that passes through it. Imagine looking through a fog bank. Distant objects appear fainter and redder than they truly are. Similarly, interstellar dust scatters blue light more effectively than red light, causing distant objects to appear redder. This effect, known as interstellar reddening, must be accounted for when studying the properties of stars and galaxies. Fortunately, astronomers have developed techniques to correct for the effects of interstellar extinction and reddening. By studying the light from stars at different wavelengths and comparing it to models of stellar atmospheres, we can estimate the amount of dust along the line of sight and correct for its dimming and reddening effects. Determining the distances to celestial objects is a fundamental challenge in astronomy. To map the universe and understand the distribution and evolution of stars and galaxies, we need reliable methods for measuring cosmic distances. This is where the cosmic distance ladder comes in, a series of interconnected techniques that allow us to measure distances across the vast expanse of space. Each rung of the cosmic distance ladder builds upon the previous one, extending our reach farther into the cosmos. The lower rungs rely on direct geometric methods, while the higher rungs utilize the properties of distant objects as standard candles, objects of known intrinsic brightness. By carefully calibrating each rung of the ladder, we can establish a consistent and accurate distance scale for the universe. This allows us to study the large-scale structure of the cosmos, measure the expansion rate of the universe, and test our understanding of fundamental physics. The first rung of the cosmic distance ladder, trigonometric parallax, is a direct geometric method for measuring distances to nearby stars. It relies on the principle that as Earth orbits the Sun, our perspective of nearby stars shifts slightly against the backdrop of more distant stars. Imagine holding your finger out at arm's length and closing one eye, then the other. Your finger appears to shift position against the background. Similarly, as Earth moves in its orbit, nearby stars exhibit a small annual shift in position, known as parallax. By measuring the angle of parallax and knowing the diameter of Earth's orbit, we can use simple trigonometry to calculate the distance to the star. The smaller the parallax angle, the farther away the star. This method is most accurate for stars within a few hundred light-years of Earth. Section 5. Standard candles, Cepheids and Supernovae. As we venture farther into the cosmos, trigonometric parallax becomes less reliable. Fortunately, astronomers have discovered standard candles objects with known intrinsic brightness that serve as cosmic yardsticks. By comparing the apparent brightness of a standard candle to its known intrinsic brightness, we can calculate its distance using the inverse square law of light. One important class of standard candles is Cepheid variable stars. These pulsating stars exhibit a direct relationship between their period of pulsation and their intrinsic brightness. Brighter Cepheids pulsate more slowly, while fainter Cepheids pulsate more rapidly. Another crucial standard candle is the type Ia supernova. These cataclysmic explosions occur when a white dwarf star accretes matter from a companion star and exceeds a critical mass limit, triggering a runaway nuclear explosion. Type Ia supernovae exhibit a remarkably consistent peak luminosity, making them excellent standard candles for measuring distances to distant galaxies. Section 6. Baryon, acoustic oscillations, echoes of the early universe. Beyond the reach of standard candles, astronomers rely on other techniques to probe the large-scale structure of the universe. One such technique utilizes baryon acoustic oscillations or BAO subtle imprints in the distribution of galaxies that originated from sound waves propagating through the early universe. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma of protons, electrons, and photons. Sound waves, driven by gravity and radiation pressure, propagated through this plasma, creating regions of slightly higher and lower density. As the universe expanded and cooled, these density fluctuations became imprinted in the distribution of matter. Today we observe these imprints as subtle variations in the clustering of galaxies on very large scales. The characteristic scale of these BAO features serves as a standard ruler, allowing us to measure distances across vast cosmic distances. Section 7. Challenges and uncertainties in cosmic measurement. Measuring cosmic distances is not without its challenges. Astronomers must contend with various sources of uncertainty and systematic errors that can affect the accuracy of their measurements. One significant challenge is dust extinction. As light travels through the interstellar and intergalactic medium, it can be scattered and absorbed by dust, dimming the light from distant objects. If not properly accounted for, dust extinction can lead to underestimates of cosmic distances. Another challenge is metallicity, the abundance of elements heavier than helium in stars and galaxies. Metallicity affects the intrinsic brightness of stars and can introduce uncertainties in distance measurements using standard candles. The expansion rate of the universe itself, known as the Hubble constant, has also been a source of tension in recent years. Different methods for measuring the Hubble constant have yielded slightly different values, leading to what is known as the Hubble tension. Section 8. Illuminating the cosmos. Light as our guide. Despite these challenges, light remains our primary tool for exploring the vast expanse of the universe. Through the diligent efforts of astronomers and the development of increasingly sophisticated telescopes and instruments, we continue to refine our understanding of the cosmos and our place within it. Light has revealed a universe far grander and more awe-inspiring than our ancestors could have imagined. It has shown us the birth and death of stars, the collisions of galaxies, and the echoes of the Big Bang itself. As we continue to peer deeper into the cosmos, light will undoubtedly guide us to even more profound discoveries, illuminating the mysteries of the universe and enriching our understanding of our place within it.